Hello everyone and welcome to a very special breakdown. Today, we're going to discuss a civic challenge solved with code. The drainage system flood alert indicator. Flooding is one of the most common disasters in urban areas, and when it happens, every second counts. With smart monitoring and predictive logic, we can reduce damage and protect lives. Our team built a complete Python-based simulation to demonstrate how real-time data can support fast, life-saving operational decisions. I'm your host, Thea, and with me today are MJ, Maricel, Cristel, and Macy. We'll walk you through the system's uniqueness, its core features, and a live simulation. Let's start by looking at how the code itself is designed.
The entire system is built using Object-Oriented Programming or OOP. This allows us to model real-world infrastructure in a structured and scalable way. The fundamental unit of our system is the drainage zone class. You can think of each object as a real drainage segment, such as a street, a canal, or a catchment area. Each zone has its own capacity, current water level, and alert status. This separation makes the system flexible because adding a new zone only requires creating another object, no major changes to the core logic. The most vital function is how we calculate alert status. Instead of relying on raw water volume alone, we compute a percentage using this formula. Percentage is equals to current level over capacity times 100. This makes the alert intuitive and consistent across zones of different sizes. Based on that percentage, the system assigns clear thresholds: 50% per trigger caution, 85% triggers danger, and 95% or above triggers critical, indicating imminent overflow. To make this easy to read at a glance, we use the display bar method, which combines Unicode progress bar and emojis. Even without technical knowledge, anyone can instantly understand the situation.
Tool focuses on interpreting what the system tells us. One key feature is automation. Every time water is added to a zone, the system immediately runs a check alert functions. There's no need for manual checking. The system reacts in real time. When a zone reaches danger or critical, the system automatically records the event with a timestamp in the alert history. This is important not just for emergencies but also for a long-term analysis and accountability. Another powerful feature is forecasting. If a zone is already at 85% capacity and rainfall intensity is high, the system estimates the time to overflow. This is calculated using the current fill rate derived from rainfall intensity and remaining capacity. Instead of reacting after flooding occurs, we can act before it happens. The system provides flexible outputs. We can generate a clean text report for quick review or export the live data as JSON. This allows integration with dashboard's external monitoring system or even future machine learning models.
This is the Python program for the drainage system flood alert indicator. First, we must simulate heavy weather conditions. We select option 5 to set the rainfall intensity to 8 out of 10, which represents very heavy rain. This immediately increases the flood rate variable across all zones. Next, we select option 6, auto simulate running 10 cycles. Each cycle adds rainfall automatically and the screen updates in real time. You can see water levels rising, alert statuses changing, and progress bars filling up. In total, 16 liters of water are applied to each zone per cycle. Notice how the main, street, and market district zones fill up faster. This reflects their smaller capacity or more flood-prone locations, and there is multiple zones have now reached critical, exceeding 100%. The system clearly displays an overflow imminent warning.
Based on the alerts, our priority would be the market district. We immediately deploy mobile pumps to reduce water levels. Using the program, we select option 2, drain system, then choose drain all, and input 150 liters to represent a large-scale intervention. Once is successful, the water level drops dramatically, and the zone returns to the safe tier. This buys valuable time for field crews to manage remaining water and prevent damage. On screen, you can see the level fall from over 100% to 0%.
Now that the storm has passed, we evaluate the aftermath. The statistic view summarizes the entire event. It shows the total rainfall received, highlight the most at-risk zone, and helps planners identify areas that may need upgrade. We access this using option 7, view statistic. We can also review the alert history using option 4. This shows the exact timing of every critical alert and drainage responses, creating a reliable audit trail for performance evaluation and future planning.